we now want to show you how to derive the kinematic equations just using the definitions of velocity, acceleration, and another definition of average velocity. Okay, and this is the algebraic way to do things, so we're not going to use any calculus in this video. Now, we've already seen that the definition of velocity is change in position over time, and acceleration is change in velocity over time, and I'm dropping the delta on the time because I'm assuming that our stopwatch is going to start from 0. And notice that I've put this bar, okay, over the V, and that bar just simply stands for average. So all I'm saying is that the average velocity is equal to the displacement over my time interval. But if I'm accelerating, and again, these equations hold, okay, for uniform acceleration. If I accelerate, then that means I have an initial velocity and a final velocity, and so the average of those velocities can also be the initial plus the final divided by 2. Okay, so we're just using the basic definition of the average. So these two quantities actually mean the same thing. Okay, and we will actually use that property here shortly. Now, the first kinematic equation we can derive by just looking at the definition of acceleration. So what the goal here is to use this equation and solve for VF, okay? And that will give us the first kinematic equation. And so if I do that, if I multiply both sides by t, then I get this, and then if I add VI, I arrive at the first kinematic equation, and I'm going to put my kinematic equations in circled numbers, okay? Now, one thing to note here is this equation has the form y equals b plus mx, okay? So the first kinematic equation is actually the equation of a linear line if we assume that our acceleration is constant, and for almost all of our cases we will, okay? The harmonic oscillator is a special case, but in general, most of the motion that we will look at, we will assume constant acceleration, and if we do so, then this has the equation of a linear line. What that means is, just as velocity was the slope of a position versus time plot under constant velocity, the acceleration is going to be the slope of a velocity versus time graph, okay, assuming constant velocity. Okay, so here's the first kinematic equation. The second kinematic equation, we're actually going to use these and eliminate some things, okay? So the first thing we're going to do is actually equate these two equations. So I'm going to say that delta x over t is equal to vi plus vf over 2. Okay, and now what we can do is actually use our previous result, this result for vf, and eliminate VF here. So I'm going to plug in VI plus AT in for VF right here. And if I do that, I'm going to get this. Okay, so we have this, and now I have a VI and a VI, so I can add those. And now I'm going to multiply both sides by t. Oops. So remember, if I multiply through by t, I have to multiply each term in here by t. And what that's going to do is put a t here and put a t squared here, okay? And now I can get rid of my fraction. Each of these individual terms in the numerator is going to get divided by 2, But since I have a 2 here, that gets rid of that. And then I have to also divide the AT squared by 2. So I put a 1/2 there. And so this is the second of the kinematic equations. Okay? Delta x equals VIT plus 1/2 AT squared. And we can make that look just a little bit nicer. And there we have it. There's the second of the kinematic equations. Okay? So to save up some board space, let me just summarize what we've got right here. The first one, VF VI plus AT. The second one, delta x equals VIT plus 1/2 AT squared. And to derive the third equation, okay, what we're going to do now is we're going to actually eliminate t from these two equations. And we're going to eliminate the average velocity as well. Okay, we're going to eliminate the average velocity as well. So what we're going to do to start is I'm going to put t up here, all right, and divide by v average. So we haven't actually derived 3 yet. So let's start with this equation, and we're going to say that t is equal to delta x over v average. Okay, so I've just rearranged this equation. What I'm going to do now is insert that equation for t into here. Okay, so we're going to have a is equal to VF minus VI over delta x times V average. Okay, but if I have a numerator divided by a complex fraction, that is the same thing as saying this. Okay? Hopefully everybody followed that step. If I have a complex fraction, I can move the denominator of the bottom fraction up to the total numerator of the entire expression. Okay? And now what we're going to do is insert the expression for average velocity. So I'm going to insert VI plus VF over 2. And now what we can do is if we multiply our numerators and multiply our denominators, we can FOIL this. And if I FOIL this, I see that I get a VF times a VI, but I also get a negative VF and VI. Okay, so those two terms will cancel out. But what I will see is that I'm going to have a minus VI squared and a plus VF squared. Okay, so in the numerator, I'm going to have a VF squared and a minus VI squared, right? And this is going to be divided by 2 times delta x. And now, if I multiply both sides by the denominator here, okay, I get that. And this is the way it's typically written, okay, 2a delta x. It doesn't matter the order of the multiplication, but that's typically the way it's written. And then I can add VI squared to both sides. And we arrive at our third kinematic equation, okay? So that is how to derive the 3 kinematic equations. You could derive a 4th kinematic equation, okay? Now, let's summarize what we've got and talk about what the other one would be. So our first kinematic equation ignores position. Our second kinematic equation ignores final velocity, and our last kinematic equation ignores time. Okay, you could derive another equation that looks something like this. Okay, but instead of VIT here, it would have VF times t, and what it would actually be is VFT minus 1/2 AT squared. Okay, but that's typically not as useful as this equation, because more often than not we want to find final velocities, or we want to find positions knowing what the initial velocity is. If we're talking about free fall, if we're talking about gravity, then the initial velocity will often be 0, because I'm simply going to drop something. Okay, so that's why this one is useful. Now, one other thing to notice, okay, what is the shape of this graph? Okay, so if I have an object and it is uniformly accelerating and I want to track its position with respect to time, then this is a parabola. Okay, I'm going to get a parabola if I track an object's position with respect to time. We already said this is a linear line. Okay, now this does not have a nice form the way that the other two equations do. What you would do if you wanted to plot an equation with, or if you wanted to plot data, in other words, and try and fit it with this equation, what you would typically do is record your velocities as a function of position, right? Knowing what your initial velocity would be, and then what you would do is then square your velocities and plot v squared versus position, and then this would have the form y equals b plus mx, right? And your m would actually be twice the acceleration. Okay, so that's one trick that we may employ later on in the laboratory. But in any case, okay, this gives you a derivation of these equations, where they come from. We've already seen a couple of examples on how to use them, but these are of paramount importance. We will come back to these again and again and again throughout the semester, so I highly encourage you to maybe create an equation library, a place to write all the important equations down. These would certainly be included in that library as well as these should be. And also, when we get into Newton's laws, definitely F equals ma, kinetic energy, and so on and so forth. But just something that you have easy access to your equations, so that you're not flipping through your notes all the time to try and find the appropriate equation. Okay? So I hope you followed all of that, found it helpful, and we'll see you next time.